Episode 77, A Night in the Life of an Astronomer. And welcome back to another edition of the Syzygy podcast. My name is Chris Stewart, and joining me on the other side of the planet again, Dr. Emily Brunsden. Emily, how are you doing?
Hello. I'm doing very well.
Good. I can see you through the Zoom, through the magic of Zoom, and you are once again in your observatory down there in New Zealand.
That's correct.
Just give us a little reminder, where are you?
So I'm at the University of Canterbury's Mount John Observatory, which is kind of in the middle of the Southern Alps of New Zealand, above a teeny tiny little township called Tekapo, and just enjoying the nice southernness here. I would say enjoying the nice skies, but tonight I'm afraid the weather has really packed it in, and we've not only got clouds,
Oh dear,
but we've got rain and we've got wind as well. So
that doesn't sound good. You should have picked radio astronomy, I think, if you're concerned about that. And can I also say, by the way, like I've been to New Zealand a couple of times, and I seem to remember that the South Island particularly does get a bit of bad weather. You know, it does get some pretty serious storms rolling in off the Tasman Sea between New Zealand and Australia. At least it did the couple of times I was there. We had the most amazing storms. And so I'd kind of think, if you're an observational astronomer in New Zealand, you must be a bit of a masochist. Is that fair?
Well, it is. I guess it depends where you put your telescopes, right? So where I am located is actually the spine of the Southern Alps. Yeah, the big Southern Alps, the ones with Mount Cook. You know, these 3,500 to 4,000 meter mountains. They're to the west of where I am at the moment, and they're breaking the weather. So that kind of the rainy half of this, or rainy side of the South Island, which is where you get your Fiordland or your Fox Glacier, Tasman Glacier, that kind of just never-ending rainy side, is doing a really nice job at generally keeping the rain away from this kind of basin, Mackenzie Basin, where I'm sitting now. So to be fair, it actually very, very rarely rains here. It's actually very dry. We do get a bit of cloud from time to time as the air pressure changes, but rain is pretty unusual.
So you're just unlucky at the moment then?
Indeed, yeah.
Well, I'm looking on the map at the moment, and it is a stunning, stunning part of the world. And listeners, if you've never been to New Zealand, when the world does open back up again, it's definitely worth putting on your list of places to visit, because New Zealand's an amazing place. And I know I don't have to tell you that, Emily. You're a New Zealand booster. But, pretty special part of the world. I'm very, very jealous right now.
Yeah, I'm wondering at what point I'm going to get the call from Tourism New Zealand for a good sponsorship deal. Hasn't quite come through yet.
Well, look, work on it. I think I'd happily put in a plug for New Zealand on every single episode of this podcast if it meant that, I don't know, we got the odd perk every once in a while. We could go and do some festivals. We could bring the fabulousness of astronomy to New Zealand. I think there's a definite deal in the making here. Work on that one. So listen, in today's show, we are going to be talking about Emily and where she is and what she's doing. We're going to dedicate this entire show to exactly what is it that astronomers do. And given that Emily is in the process of being an astronomer right now, like actually in her daily life, or her nightly life, actually, she's doing the thing. She's actually being the professional, practicing, honest-to-goodness astronomer. It's a really good opportunity to say, what exactly does that mean? What do you do for a living, Emily? So we're going to be doing that today. And I guess a place to start might be, could you just sort of take us through what's a day in the life? What do you do when you're observing?
Of course, yeah. Well, first of all, it becomes what is the night in a life of an astronomer, really. And in some ways, I'm very fortunate because I'm a bit like a classic astronomer. There are lots of different types of astronomy, as we've talked about many times in Syzygy. Some astronomers use space data. In fact, I use space data myself. Some astronomers are theoreticians. Some use radio telescopes. There's a huge kind of diversity in what an astronomer can mean. I just happen to be, I guess, what you'd sort of typically think of as the more traditional style astronomer, one who uses a telescope to look at the stars.
So that is classified as observational astronomy? Would that be fair?
That's true, yep. And indeed, yeah, optical, I guess, observational, stellar astronomy, all these kind of nice adjectives you could throw in front of it.
Perhaps what most people would imagine when they think of an astronomer. You've got an optical telescope, you're looking at the sky, in a sense, with your eyes. I mean, I know that you probably don't have your eye up to the eyepiece of the telescope going, oh, look, things, looking with your eye and spotting things and writing them. Oh, I saw another comet tonight. That's not what you do. But you are at least a bit closer than other branches of astronomy to that classical idea of, I'm going to point a telescope at the heavens and I'm going to see things.
Exactly. Yeah. And you're exactly right. I don't go up to the telescope and sort of look through and peer through it and make notes. Like, I guess that is the typical kind of example you might think of. But
we've moved on from Galilean times, is what you're saying.
Exactly. So being a professional astronomer in the sense of what I do is also a bit being an instrument scientist. It's also trying to be a bit of a weather forecaster, and all these kind of extra things that you're trying to do. But effectively, you are controlling a large scientific instrument.
So that means that if you are going to be using, light and observing in the visible wavelengths, you have to be doing that when there isn't too much other light around. In other words, you need to be somewhere where it's really nice and dark, and you need to be doing your observing at night. So you become a night owl.
That's exactly right.
So how long have you now been doing nights and sleeping days?
So I've been on this run for about 10 days now, out of 14. Most observing runs will be between about a week and 3 weeks that I do, because for a week is kind of the minimum that you could be bothered to put yourself onto night shift for a long period of time. And
it's a little bit like flying around the other side of the world. You got to be there for a while for the jet lag to be worth it.
Yeah, exactly. Yeah, and after about 3 weeks, especially in winter time when the nights are really long, then it gets really exhausting. So that's kind of about my limit.
Do you just sort of, how do you do it? We'll get onto the details of your actual astronomy in a second, but just from a lifestyle point of view, how do you make that adjustment? How do you go from, right, daytime, obviously I'm up and about and I'm doing my thing, and nighttime's clearly for sleeping, and now I've got to transition to complete, like a full 180 flip. That's got to be really hard. How do you do that?
Yeah, it can be tough. So I like to, my personal way of doing it, and every astronomer kind of has their own way to do this, but I like to arrive at the observatory. So I have a night before I have to start to observe. And on that night before, I sort of just try and stay up for as late as I possibly can. And usually that's sort of about 3 o'clock in the morning. So that's not too bad, because then because you're so tired, of course, you go to bed. And the astronomers' quarters here at the observatory are light proof, so you've got massive blackout blinds all on the windows, so there's not even a slither of sunlight that can possibly come into the bedroom. So it's nice and dark, and it's kept really, really quiet as well. So the building's quite separate from the rest of the observatory, where the tourists are kind of up there having their nice cup of coffee and things. And the other people who are working around the observatory are very aware that you've got astronomers sleeping. So they sort of stay away or try and keep quiet at least.
Does it take you a few days to properly settle into that rhythm? Are there a couple of days, again, like flying long distance, where you're sort of walking around in a bit of a haze?
I find it not too bad if I do that one night beforehand. If you try and do it just like first night, going to stay up all night after a day of, traveling or whatever to get there, then that's pretty rough. But I think I must be fairly used to it, because I sort of flick around reasonably easily. Because, once you've had one big sleep, then you can you just push yourself around if you like the clock.
Yeah. What about coming out the other end? Because I guess going into observing, right, you're moving into this strange bubble where it's okay if you're a little bit hazy, other than needing to focus on your work. It's not like you're interacting with the rest of the world in a big way. Whereas coming out the other end, you're emerging from the bubble, and you've got to go back out into the world and deal with real world things again. Is there any issues with coming out of that and having to adjust to being back in the world again?
Yeah, I normally have a bit of a grumpy day, let's call it. Lots of coffee and grumpiness as part of that day.
Steer clear of the astronomers at the end of their shifts, I think, isn't it?
Yeah, basically just get up much earlier that morning. So I might get up at kind of 11 o'clock in the morning after going to bed at sort of 6 or 7, and then I'm just grumpy for the day, but then I can go to bed at normal time.
All right. Well, if we're talking about a day in the life of Emily the astronomer then, or really a night in the life of Emily, take us through a night. What do you do? What exactly do you do, Emily?
So at the moment it's March where I'm observing. So we're not too far away from solstice. So we're coming up to, equinox. So you're coming up to the March equinox where the night is about 12 hours long and the day is about 12 hours long. Of that, we're coming up to sort of between 9 and 10 hours of observable time. So at the moment, I'm getting up at kind of about 2:30, 3 o'clock in the afternoon. Sort of meals are kind of a bit irregular when you're observing. I sort of get up and have breakfast, but then I'll probably have a cooked dinner, sort of maybe about 9 or 10 o'clock in the evening. And then have a night lunch, we call it, which is a lunch which is kind of at around 2 o'clock, 3 o'clock in the morning, something like that.
Basically, you're eating to survive. Let's not worry too much about all that. But I mean, are there sort of formal things like do people tend to gather for meals and stuff like that?
It really depends on the observatory. So I'm at a fairly small observatory where it's self-catering. So we've got our own kitchen and we can sort of just do as we want. Bigger observatories will have professional staff who will cook meals. So there'll be set sort of meal times. And you can get up, sort of have your breakfast, and then there'll be a big cooked meal, sort of again around somewhere in the evening time. And then they'll pack up for you a night lunch, which you can, depending on where you are, sometimes you have to travel some distance from that building to your telescope that you're working on. So you have your little night lunch you pack and take away with you with your sandwiches and your yogurt and things.
But you're doing your own thing. How many people are there with you? How many people are observing on in the same facility as you?
Yeah, it's pretty quiet at the moment. So it's just myself and my fiance Daniel, and we're on the 1 meter telescope. The other big research telescope is being run by the MOA team. So there's an observer who's working on that. And the other telescopes on site, one of them is a robotic telescope that does automatic observing for the American Association of Variable Stars. And the other one is sort of partially being used. Sometimes it's not currently on schedule at the moment, but and then there's a couple of smaller ones which are used by the tourism sort of groups that come up and observe the night sky.
Oh, it's nice that you and Daniel, you and your partner are working together on this one. I guess that makes it a little bit easier in that you're adjusting together. You got someone to hang out with and work with on that, who also knows your foibles and is prepared to be very forgiving.
Well, exactly.
You do have those grumpy days.
He does sometimes request me to observe his stars instead of mine, though, which is a bit annoying. But
that's a bit rude. Yeah. As long as it goes both ways, I think that's okay.
No, we're sneaking a few of his ones from time to time as well.
So that's sort of the social and logistics side. So then you've gotten up, you've had some breakfast, you've figured out what you're going to take for your night lunch, but then you get to work. So what's a work night look like for Emily the astronomer?
So, okay, if the weather's, let's say we've got a lovely clear night, the weather's nice, the wind's not too strong, then I'll be looking at opening up the dome of the telescope kind of about an hour before I start observing and sort of turning on some of the lamps and so on that I use. And the reason for that is that you want the inside of the dome, which is, the dome's protecting the telescope, but you want that inside of that dome to be as close as possible to the outside temperature, so that there's not a temperature difference, because temperature differences cause ripples, if you like, in the atmosphere, which makes your stars sort of twinkle around and dance around, which isn't so fun.
Right. So you want to get everything as close as possible to an even temperature so that you know that you've got the best chance possible of getting a nice stable image. You haven't got all sorts of weird stuff happening between it's warmer down here, it's colder up there, and that's going to make things shift around.
Exactly, yeah. So you'll see in a lot of observatories, domes will start opening kind of about half an hour before sunset in some cases, but usually on sunset at least.
You're up a mountain. Bit chilly, is it?
It is tonight. It's about sort of 7-8 degrees, but it has been reasonably warm. So I guess it's still the end of summer. So we have had some nights where it's been about 15 degrees.
Oh, that's not too bad. Yeah, of course. Here I am in York thinking, oh, it's just coming out of winter here. But you're in summer. You're down there in summer. So just another reason to be jealous. Okay, so you've opened up your dome. You've equalized the temperature. Great. Then what?
Yeah, so then you've got to sit down and start thinking about your observing program for the night. So you've got to sort of about an hour while you wait for all this to happen. We've got some lamps that we use as part of our observing. They also take about kind of half an hour to an hour to warm up so that they're nice and even and stable. You sort of work out a program, and that means you're going to sort of think about what stars are on your to-do list, and then you've got to work out, are they actually observable in the sky that night? Because of course every night the availability of a particular star will change as the Earth's rotation and its orbit around the sun changes. So you're looking for targets that are nice and high usually. You don't want to have things that are too close to the horizon, because you have to look through quite a lot of atmosphere at stars that are really close to the horizon.
Yeah. I guess looking through too much atmosphere, or the more atmosphere you look through, the more distortion you get, the more stuff is in the way.
Exactly.
So you want stuff nice and high in the sky, so you're just looking straight through the atmosphere out into space.
That's not always possible. I mean, if you really want particular stars, then you might have to sort of get them. So the work that I do, I work on a program where we've got kind of about 60 or 70 stars that we are really interested in. And so I'll sort of figure out which of those are observable at the moment, and do some nice charts of kind of what parts of the night I can observe which stars, and then that's kind of my sort of program. I can start off with this sort of selection of stars and work through those, and then move on to the ones that are later on in the night.
Nice. Okay, so we've got the telescope set up. You've got your lamps nice and warmed up, and those lamps you were talking about, like, what are the lamps?
The lamps are part of the spectrograph that I work on. So what I'm going to be actually doing is, when I start observing, is I take the light that's coming into the telescope and I push it into an optical fiber, which is a little bit like the kind of internet fibers that we have. And that fiber, it's like a little pipe that takes the light from the telescope, and it puts it about 10 meters away into a little room which is near the telescope. And in that room is an enormous spectrograph that I use. So this is my instrument that's on the telescope, if you like. And that spectrograph is going to take that light and break it up into its rainbow, its constituent wavelengths, and then we're going to do all the work that we need to from that spectrograph. But to calibrate that spectrograph, we need to have kind of knowns. It's like when you do science, you always have your standards, right? These are the things that you know what they should look like. And so we have lamps which we put into our spectrograph that we know what they should look like, and we can measure those. Right.
If you got a lamp which is shining with a very specific fingerprint of wavelengths, of colours of light, and you throw that into your equipment, you know what that's supposed to look like, and so you can make sure that everything is working properly and properly stabilised. Right.
Exactly.
Gotcha.
Yep.
So when you're talking about turning on the lamps and making sure that those are properly warmed up and stabilised, that's what you mean.
Exactly. Yep.
Okay.
So I guess when it's nice and dark, so this is... interestingly, you might have heard of different types of twilight that are used around the world. And so we have things, you think of sunset, okay, you can start working at sunset. But if you've actually watched a sunset, then even after the sun has dropped below the horizon, there's still a lot of light in the sky, right?
Yeah, it's something that I've really noticed in coming to the UK from Australia, where, living in Australia, you're a lot closer to the equator than you are in the UK, for the most part, if you get right down into Tasmania or something. Whereas New Zealand and the UK, similarly, are actually quite a long way from the equator, which means that in summer, when the days are really long, you've got these really, really, really long twilights where the sun's gone down, but there's still a lot of light around for hours. And it just never ceases to amaze me how long the light is in the sky. And then you get a bit of dark, and then it's 3 a.m. and already it's getting light again. I still get absolutely blown away by that. Does that get in the way of what you're trying to do?
Well, you just have to wait. So, yeah, as you say, it does depend on where you are in the world as to how long your twilight is. It also depends on what time of year, because it depends on what angle the sun sets at. If the sun sets at a really kind of straight up and down vertical angle, which would mean that you're on the equator and it's equinox, bang, there's your sun gone straight down, then your twilight is very short. But if you are, at other more extreme latitudes, then and it's kind of closer to either solstice, then you get the sun setting at a really long angle, shallow angle, so it stays just below the horizon for quite a long period of time.
Yeah, to that extreme where you sort of get up around or within the Arctic Circle, and for some parts of the year, the sun's just sort of circling around the horizon without ever actually dipping down below it. It's quite amazing. Okay, so you've got to not only be thinking about where are the stars or where is the star that I want to have a look at, but what else is going on? You've got clouds, which are a problem. You've got the light in the sky, which is a problem. So you might have to wait for a while in order to make sure that there's enough darkness for you to actually do what you want. This is a lot of figuring out in order to actually get onto the process of, right, I'm now ready to have a look at the star.
Yep, and you've got to make sure your wind is pretty sensible too. So
what's the problem with the wind? Why does that get in the way?
So, well, when you've got a dome with a kind of a big structure with a little small gap in it, you don't really want to point that in really strong winds, because otherwise the dome, which was on top of the mountain on the top of your telescope, will end up at the bottom of the mountain in the lake, and that's not a good thing.
Does that ever happen? That's got to be bad.
I think domes have blown off observatories before, but yeah, I mean, it's not good for the equipment, obviously, to be shuttered around. You get too much dust in the dome and things like that. It's just not a good idea.
So have you got parameters to work to? Like, is there there's a wind gauge that says, yep, you're okay. Nope, don't open it. Just go back and have some lunch.
Yeah, every sort of telescope and dome has its own kind of limits. We actually have quite a high limit because we're a bit sheltered here. I mean, the actual mountaintop is one of the windiest places in New Zealand. It has recorded, I think, which is still New Zealand's highest wind speed record, which was around about 220 kilometres per hour winds.
What? That's insane. But you're not up the top of the mountain. You're sort of only part way up.
Well, we're very close. It's just that we're just slightly sheltered here. So we actually operate up to something about, well, if it gusts above 60, then, or if it's consistently above 40 kilometres an hour, then I'll close. But that's actually quite a lot of wind, really.
Yeah.
And many observatories will be much less than that. Sort of just depends on the telescope and the dome structure.
Yeah. But you were saying it's pretty windy tonight, so
it has been
windy enough to say, no, we're not opening this thing. It's not happening.
It was before. It looks like it's calmed down quite a lot now, but the rain sensors are still going off. So
right,
I don't think I have to run away and open up just at the moment.
Yeah, because opening with the rain coming in, I guess, is not a good thing for the equipment either.
No, that's really not a good idea.
Rats. Okay, well, let's go back to assuming that the weather is good, that the wind is behaving itself, and that it's not raining, and then you've got clear skies, and you've figured out that there's a star which is in the right kind of direction, and it's dark enough. So, that's a big build-up.
Yeah.
What do you do then?
Well, it's one of the most fun things is you go into the dome and you switch on all the telescope. That's one of my favourite parts of the whole thing, just because there's this big kind of instrument panel on the back of the telescope. It's got these big switches, and you go boom, 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 boom. You can put all in the switches, and you get this big hum of the machinery just going.
That's great. I mean, that's the sort of equipment that every scientist just wants, even if it's got nothing to do with what you actually do research on. You want the big machine with all the switches and the hum. Has it got one of those switches which is sort of, it's your big lever switch?
Ka-chunk? I wish it did.
You should just bolt one on, even if it doesn't do anything. Just a ka-chunk, now we're ready to go. I think that'd be great. So that's good. So there's a big build up to now it's time to switch the thing on, and you're ready. is it? I was about to say, does it hum and vibrate? It wouldn't vibrate. Vibrations are not good for telescopes. No. Okay, so no vibration, but a hum. So that's good.
Yeah,
all right, you turned it on.
Yep.
Excellent. We're now ready.
And we can open up the mirror shutters, which are, there's the telescope I'm working on has a 1 meter diameter mirror. And that mirror is the most precious part of the telescope, really, because that's your shiny bit. That's the bit that's collecting all your photons for you. When the telescope's not in use, then we have these nice little shutters that come across and just cover up the mirror. So, if dust doesn't go into it, or if you're opening and closing the dome, then if something accidentally fell off it, then it's not going to damage the mirror, that kind of thing.
Get a screw falling onto your mirror probably wouldn't be good. I mean, I'm just having a look at the website here. So this is the Mount John Observatory from the College of Science at the University of Canterbury facilities page, and you're working on the 1 meter McClellan telescope, yes?
That's right, yep.
Okay, so it says here, the optics of this 1.00, so very precise to 3 significant figures, 1.00 meter Dal-Kirkham reflecting telescope were polished by optical engineers from DSIR's Physics and Engineering Laboratory. So right there, that's the first sentence about the research facility is, who polished the optics? I'm guessing that this is a big deal. That, the mirror is the important bit, right?
Absolutely, yeah. And the optical quality of your mirror will tell you basically how bright or how faint a star you can look at is.
Right. So is 1 meter, explain this to someone who just doesn't do this. A meter, I'm holding my arms apart, that's about a meter. And that feels to me like a sizable bit of mirror, right? Is that big? Is that big for a telescope? Is that actually pretty piddly for a telescope? How big is that?
Yeah, it's interesting. So it's on the scale of, world-class research instrumentation. It's on the small side. So the biggest optical telescope in the world, which we've talked about a few times, is SALT, which has an 11 meter mirror, although that's made up of lots of little individual segments. The biggest, I think, single mirror telescopes are about 8 meters across. So that, those are enormous structures. So a meter is kind of on the sort of lower end of that scale. But that being said, I guess in terms of telescopes that it's a big thing, and it's something that we get a lot of time on, which is really where we get a lot of value in this, because I'm doing time series work. I want to observe my stars not just once, but hundreds of times over many, many years. Then you just couldn't do that on one of these amazing world-class big telescopes, because
right. So it's a balance of trying to get time on the biggest mirror you can possibly get, because big is always better. But the bigger it is, the rarer it is. It's less likely that you're actually going to get a look in at all. And so you compromise and say, all right, let's do this one, which happens to be in New Zealand where I come from, so that's good. And it's big enough to do what I want to do, but it's, modest enough that I can actually get some decent time on it.
Exactly.
Is that the idea?
Yeah.
Yeah.
And what's great about this particular setup is that it's actually got a really high resolution spectrograph on it. And it's unusual, I think, it's fair to say, in the world to have such a high resolution spectrograph on a smaller telescope like this. Normally you'd expect this kind of spectrograph to be on a sort of 2 to 3 meter class telescope.
Right.
So we get a really nice instrument on a smaller telescope, but we get a lot of time with it.
Nice. You've just sent me through a picture of this thing, which will if you're looking at your podcast player now and it shows chapter pictures, chapter art, then you should be able to have a look at it now. That's a pretty funky looking device. I'm trying to figure out what I'm looking at here. So there's a sort of big green T-bar bit, right?
Yep.
And on one side of that, you've got what I'm assuming is the telescopy bit, because it's kind of long. It's got some stuff down the bottom and some stuff up the top, and that looks to me like a telescope with the outside taken off it. So we can talk about that in a second. On the other side of the green T-bar bit, there's what looks like a big wheel or something. What is that? Is that a counterweight? What
exactly,
is that?
Yeah. So that's the counterweight for the telescope. So if you think the big green T-bar that's in that image, if you look at where that's pointing in the sky, it's actually pointing towards the south celestial pole. So the reason for that is that you might want to have these what we call equatorial mounts, is that means that when you're tracking a star across the sky, because all stars appear to rotate around the celestial pole. In the northern hemisphere, it's the north celestial pole, and the southern hemisphere, it's south celestial pole.
Makes sense.
And so when you if you build a telescope with this style of mount, you actually only have to have your motors driving in one direction,
right,
to keep following a star as it goes around the celestial pole.
Makes sense. So that's why that's sticking up at that funky angle like that.
Exactly,
yeah. Because that means you only really have to rotate it in one plane. You're not making adjustments in 3D. It makes the problem a little bit simpler for much of the time. Cool. Okay, so that's your telescope on the other side, and your 1 meter mirror. Where's that? Is that down in that bottom?
It's in that
bit?
black sort of bit. Yeah. So that's the mirror cell, where it's kind of this black sort of tiered structure in there.
So what's up the top there then? Up the top above that?
Yeah. So you might see a black tube at the top.
Yep.
That's holding the secondary mirror. So this mirror is a Cassegrain focus, which means the light's collected by the large primary mirror, the 1 meter primary mirror. That's then focused towards the secondary mirror, which is in that up at the top of the telescope. And then that secondary mirror, which is usually a convex mirror, then refocuses the light back down towards the primary through a tiny hole in the middle of the primary mirror and out the back of the telescope.
Right. So it's coming in, hitting the bottom, bouncing up to the top, coming back down through a little hole to where your instrument sensors are sitting, waiting to collect the light.
Yeah. So again, the benefit of this is mechanical. It means that you can put any heavy instrumentation on the bottom of the telescope rather than at the top, and that makes it a little bit more stable, a little bit less susceptible to things like wind and so on.
Sure.
But when it comes to the work I do, so it's not in the photograph that I showed you, but there's actually, instead of having an instrument bolted onto the back of the telescope, there's just a fiber. So there's a little black cable which just plugs into the back of the telescope that collects the light, and that cable just takes the light over across to the spectrograph.
Nice. I'll put a link to all of these images in the show notes, but that's a lovely image. And I'm just trying to figure out the scale here. Looking in the background of that picture, there's a ladder against the wall and a couple of what look like cupboards and things. So I'm guessing that this whole structure, I mean, the dome itself, that's got to be what, like 7-8 meters high? I mean, this is a big hunk of kit.
It is, yeah. So the telescope itself is pretty. What are we getting? Like 3 meters, but 3.5 meters tall. So it's much taller than me. Just the counterweight system is probably mostly my height. It's a big instrument. And what's really cool is that the design of this telescope is that the floor of the whole room actually moves up and down.
Why? That feels weird.
That's a good why. So it's actually really useful. It's for a lot of reasons, but one of the main reasons is that we actually means that you can bring up the floor to be close to the telescope when you're working on the instrumentation. If you need to do things like change the instruments, change the mirrors, because we do change the secondary mirror, for example, reasonably regularly for different observing programs. And we change the instruments to a suite on the back of the telescope. Sometimes those instrument suites can be really heavy, so you can actually just have them in a cradle and have the floor come up to meet the telescope, bolt your instrument on, and then have the floor drop away again. And the reason why you want to obviously have it drop away again is when the telescope's moving around, you don't want anything, you don't want to hit anything, so you want to keep everything well away from it.
I'm just looking through these photos that you've sent through, Emily, and there's like beautiful views out across the mountains and stuff here. What a horrible place to work. You must really suffer as you're doing this stuff.
Yeah, it's not bad. It's not bad. I mean, let's be honest. It's not necessarily easy work either. So I've had a few nights in this run, for example, where we've had. When it's clear, it's nice because you can just sort of point your telescope and you can say, go and find me the star and have a look at it, and you set up all you're observing, and you can sort of sit there and watch it, but it's easy, like everything's working well, it's fine.
Yeah.
So I don't actually do my observing in the dome with the telescope because it's cold and dark and not that friendly. So we have a data room, which is right next door to the the dome, and from that data room, I generally control most of the time the telescope and the instrument, and sort of tell it, where to go. And I might go and check on it, every hour or so just to make sure it's doing its thing. But
sure,
most of the time I'm working here in the data room, which is where I am now.
So let's talk a little bit more about that process of how you actually do the observations and what you're actually recording. So you've got your great honking telescope out there. It's got a tiny little optical fiber cable coming out the back of it, which is then taking the light that's come into the big mirror and then bounced up to the smaller mirror and then gone through this tiny little hole into your instrumentation and ultimately coming out through a fiber. Then what? Right? With dot, Emily gets Nobel Prize. So what are you actually measuring? You're looking at a star. You found your star. You've locked onto it. We're going to get the light from that star and we're going to put it in this tiny little cable and send it off to do what?
So we want to get a spectrum of this star. Mm-hmm. So the work that I'm doing at the moment, spectroscopy, is we're taking that light of the star and breaking it up into all the different wavelengths. Now, if you took a prism, for example, and you took a spectrum, that's making a spectrum of the sun, right? You're getting the nice rainbow that you get just from a nice sunny day. Now, the way that we do that with sort of this particular instrument is we do that, but on a much, much higher resolution scale. So imagine taking that kind of, few centimeters of rainbow that your prism generates and turning that into many meters worth of spectrum so that you get the resolution of detail of all those colors.
Right. So you're zooming in and zooming in. What we see as a rainbow is, smearing out of all of those colors in the sunlight. But if you zoom in enough, then you can actually see detail in that spectrum.
Yeah.
And just remind us what that detail is telling us.
Yeah. So what we're doing is we're taking that really long sort of drawn out spectrum. Well, first of all, we have to try and take an image of it, which is, okay, you don't tend to find CCD cameras that are kind of several meters long. That's
not easy.
No. So what we do is we actually stack it. So we just sort of say, chop, put the next bit underneath it, chop, put the next bit underneath it. So we stack it so it's actually a square, which is much easier to work with.
So you're breaking up this spectrum into individual chunks so that you can zoom in on it more.
Exactly, yeah. So if you go from the top left of an image down to the bottom right, you see just lines, which are the spectra, going from sort of the red at the top to the blue at the bottom. And in that, what we're looking for is we're looking for the spectral lines that come from the star itself, which will be present. So the star produces its own rainbow, just like the sun, of just what we call an emission spectrum. It's just a rainbow, all the light. But then there are bits missing out of that rainbow. And the missing bits come from where you have atomic species in the atmosphere of the star itself, which are actually absorbing the light. So the light is produced in a perfect rainbow from the center of the star, but as it travels through the outer layers of the star, some of that light of very specific wavelengths gets absorbed by some of the chemical elements that are present. So things like iron or magnesium or silicon or whatever it is in the atmosphere of the star will just take away tiny little slithers of that spectrum.
Right. And so because each chemical element has its own very, very specific set of those absorption lines, its own fingerprint in the spectrum, then you can sort of eyeball that or computerize eyeball that. You can apply some data analysis to it to say, all right, can we see evidence for iron or can we see evidence for, insert chemical element here? But what you're seeing in that spectrum are these tiny little gaps, these lines, these absorption lines in the rainbow. So there's a little dark gap there.
Yeah, exactly. And so what I want to measure is I'm measuring how the surface of the star changes over time just by the fact that there's a pulsation, a motion happening on the surface of the star. And so motion means a Doppler shift. So if you've got something that's moving relative to you, then the stretching or the compressing of the photons as that movement happens actually changes their color from being slightly blue to slightly red, So when they're coming towards you, they're slightly bluer. If they move away from you, then they become slightly redder.
Right. It's the light version. It's the color version of your classic, car going past, your racing car going past, and do that as it goes past. You've got the high frequencies as it coming towards you, and then that shifts down to a lower frequency as it goes past you and recedes from you. Even though the car is making the same sound all the time, we hear it as high and then low. That's an audio Doppler shift. You're talking about a light Doppler shift. And the surface of the star moving does the same thing with the colors of the light, with the spectrum.
Exactly. So those little lines will just move very slightly in position as the surface of the star changes. So they might become a little bit redder as the surface of the star kind of recedes from us, and then they might become a little bit bluer as it comes out towards us. And so it's that movement, the left and right movement is translated into the spectrum that I'm trying to measure.
And you said earlier that you're looking at a time series. You're observing over a period of time. It's not just a single snapshot. There's a picture of the spectrum of the star. You're observing that over time. And so presumably that's why that you're trying to see those changes, those shifts, to be able to figure out how the star is wobbling?
Exactly.
How the surface is moving over what kind of timescales, how rapidly, that sort of thing?
Exactly. Yeah, the first question we want to measure want to find out is how often, what's the frequency or the period of each of the pulsations. And then there's several of them, the stars that I study, overlaid on top of one another. So you need quite a bit of data to disentangle the fact that there's several things happening at the same time.
Yeah, I mean, there's, you can think about the fingerprint of iron, for example, the spectrum, the absorption spectrum of iron, just as one example. But there's loads of things in stars. Like, stars are really complicated. So not only have you got lots of these lines in the spectrum all overlapping with each other, so you've got to sort that out, but then you've got the star itself doing lots of different things at once. Like, that's got to be a data nightmare, Emily.
Yeah, well,
how do we sort that out?
We do, and we make it even harder for ourselves, because it sounds quite nice that I study stars that have these periods which sort of are between maybe about a third of a day, so 8 hours, up until about 3 days. That's sort of the typical range of periods. So you'd think that, well, I can just sort of sit on a star for 3 days in a row, and then I get, most of a cycle, right? The problem is that actually spectroscopy comes with a trade-off. So even though you can take a measurement of a star, to get a good enough spectrum to make a really high quality measurement of the tiny, tiny shift in the speed, for most of my stars takes between 20 and 30 minutes to get one spectrum.
Right. And so when you add up those 20 and 30 minutes, suddenly there's limited numbers of those that you can do in any given evening.
Well, exactly, yeah. And so this is a bit of a program of patience, if you like, with these stars. And we'd maybe sort of 100 or so observations to start proper analysis of what a period of a star is. So that takes a while to gather that amount of data for just one star, let alone if you've got a program of sort of 60 or so of them.
So is that the sort of program that you're looking at on this run? Like, how many stars? Ideally, let's assume the weather has behaved itself, which we'll get to in a second. It hasn't really been doing so. What would have been the best case scenario? How many stars would you have collected data for?
So I've got about 7 or 8 that I'm working on at the moment, and I'm just trying to build up the numbers on these ones. When I was doing my PhD work, it was a bit more focused, so I was interested in 2 or 3, and I'd just come down and I'd just hammer those particular stars. So I'd do like 1 star for most of the night.
Beat it into submission.
Exactly, yeah, just get lots and lots of data. But now we're sort of trying to work on just sort of a more general program and getting observations of these stars. Just a few a night is what we're trying to go for at the moment. At the same time, we've also got some interesting binary stars that are in our sample that we are on kind of what we call a long-term monitoring program. So binary stars, 2 stars that are orbiting each other, they also show these same or similar signatures in their spectra, because sometimes that one star's moving towards you and sometimes it's moving away from you in its orbit. And these orbits of binary stars can be anything from a few days to hundreds of years. And some of the stars, we don't know what the orbits are. So we kind of, once in a while, we'll just take a spectrum of it to see, add another one to the list to see if we can try and nail down, is this a 100-day orbit? Is it 120? Is it 1,000 days?
some of it's really sort of exploratory. There's a system, but we don't really know yet. So let's just keep taking pictures of it, and eventually, with luck, we'll figure that out.
Yeah, exactly. Yeah.
But with the other stars that you're looking at, the ones which are sort of, wobbling and pulsating and so on, what is it that you're trying to find out here? You've got your set of stars that you, Emily, the astronomer, you're interested in and you want to find out, and you're looking at them and you're taking this data and you've got your spectra with all the lines in it, and you're taking that over a period of time. So at the end of the day, what is it that you want to turn that into? What are you trying to find out?
Yeah, so we're trying to understand the nature of the pulsations themselves, which is really, really important, because the pulsations are not just things that happen on the surfaces of stars. In the case of these pulsations, they also dig down really deep into the interior of the star as well. And so if we can understand, just beginning with, say, the periods of the pulsations, how many pulsations are on the surface of a particular star at a particular time, and how big the amplitudes are, then that's a start to therefore understanding, well, that's a pulsation that we can see on the surface, but it's come through all these layers of material on the inside of the star, carrying that information with it as well. So that's a really unique kind of probe into the interior, when you can't just kind of stick other things into the interiors of stars.
Right. So you're using the wobbles on the surface as a way to sort of dig into, but what's happening under the surface? What can we learn about the structure and the dynamics of this star from what we can see? Because, we can only see what we can see. So what can we work out backwards from that?
Exactly, yeah.
Right. That's a lot of data. I'm guessing there's a lot of analysis that you've then got to do. I guess what I'm trying to get at, Emily, is how do you go from, I've got a bunch of data that I've just taken with my telescope. That's what you're doing right now. You're collecting data. What do you then have to do with that in order to get to the understanding, the paper, the publication, the theory, the glory, ultimately the fame and the awards? How do you get from the observation that you're doing right now, this part of your job, to the other parts of your job? What do you do then?
So, I mean, it's a very good question, and it's not one that we always get to the end of, if that makes sense, because you sort of start off with a star, and sometimes you get kind of a really nice kind of solution. It says, okay, we figured out the star has this periods, they're working in this kind of geometry, so this is what the surface of the star must look like. Therefore, we can apply these stellar models to understand what the interior must be doing. Now,
great.
We've got
easy job done.
We've got some stars we can do that with. Not so much done in spectroscopy, but done with things like TESS, which is the other thing I talk about a lot that I work with. Or Kepler,
that's the satellites, the space telescope.
Yeah. But we're still trying to understand the relationship between what does the information from the space telescopes tell us and what do the spectroscopy tell us, because they're probing slightly different parts of the star. They're probing them in slightly different ways. So there's a real opportunity to learn what is the difference in the physics that the two things are trying to tell you. So that's actually a big part of the PhD project of my student at the moment, is trying to match those two and sort of say, well, this is probing this physics, this is probing this physics, what's the same and what's different?
Right. So you've got to be able to sort of merge together the information that you're getting from your observing runs with information that's being gathered in other ways with the underlying, astronomical or physical theories that you've got, and you've got to try to sort of piece all of that together into something that's, okay, if we do it that way, that's beginning to make sense. Like, I can see how that works ultimately as an understanding of this distant star that we're observing. It kind of all fits. If you're lucky, you can make that work. You can get that all sort of joining together.
Do you hear that beep?
I can hear that beep.
Oh,
yeah.
Let's stop for a minute. That's the rain sensor.
Right. That's telling you that it's now absolutely pissing down outside?
Yeah,
Is that
that's telling you really just don't even think about opening that door right now.
Stay where you are, record another podcast. Just is not even worth it. Yeah.
Yeah. So, I don't think there's a chance of me having to rush away just in the next few seconds, but I can turn that off if we need to.
If that's okay, that's probably a good idea.
I think so.
I think you know what it's saying. But no, I just asked you the question about the way you're bringing together all of these, your data and other bits of data, and the physical understanding into, if everything goes well, then you get some insight into this particular star. But that's the process, is that there's a lot of work that then has to happen in order to get from the observing run that you're doing now through to some kind of endpoint of, okay, we think we've progressed our understanding somewhere.
Yeah, exactly. And then you've got to try and match your star to the models. So our models of stars on the interiors of stars are good. I mean, I don't want to kind of tear apart our models, but
don't tick off the modelers here, Emily.
No, I'm not going to make them upset. They're good, but they're not complete. I mean, everyone, I think, knows that they're simplifications of what we see. Yeah, exactly. But there's a lot of things that we don't know how much to do. Like when you have different areas inside a star, different regions, how big are those regions? How much mixing happens between those regions? How big is the core? These are kind of quite fundamental questions, but things that we don't have definitive answers for. So the ultimate goal is to take the observations that we're making, put those together with really good, sophisticated models, improve the models, of course, using the data, because stars are always right, as some of my colleagues like to say.
That's a nice way of looking at it. The star's not behaving. So, well, no, the star is doing the thing that it does. It's our job to work out why.
Exactly. And then try and put that into a larger picture of how stars evolve throughout their whole lifetimes and how we can understand that process. And these stars that I study will just be a very small kind of contribution towards that big goal.
Nice. And so, as you say, ultimately you've got to get all of your stuff merging with our understanding from the models. But then the next step along from that is maybe from the observations that you make and the findings that you get, the models get adjusted because, okay, well, that now gives us a bit more information to be able to adjust things and figure out what is going on inside stars. It's a fun process. It must be, I don't know, when it all goes well, it must be very satisfying.
It is, but as with any kind of research, when it all goes well, is also, well, first of all, that almost never happens, but every star seems to be different and unique in its own sort of weird and quirky way. And that actually ends up bringing up whole new questions that you never even thought to ask before. And so you can go down lots of rabbit holes along the way, just trying to figure out, okay, well, this star's been doing things a bit differently. We don't understand that. Let's try and figure out what that star's doing. And then you build extra understanding from taking that sort of in-depth analysis of that particular star. And then so you keep building on this. So even when you set up a research program, we're going to do X, then we're going to do Y, then we're going to know Z. Actually, it turns out there's a whole bunch of other letters that you never even dreamt of in between in that process to try and get you to, even if you do get to Z, and if you do, then you're doing really, really well.
So, everything that we've talked about for the majority of this podcast, Emily, has been around all going well. We're able to open the dome and point the telescope at the sky and take the data and then figure out what it means. But what do you do when, you've lined up a week, 10 days, however long it is, at an observatory and it's not going well? The weather's not behaving well. You've got rain, you've got wind. You can't do the thing that you'd allocated time to do. What happens then?
Yeah, so if you're really closed, if you're not able to do anything like I am tonight, then you can do things like record your favourite podcast. Or indeed just
It's the only reason we do this, isn't it? It's just to keep you occupied when the observatory's closed.
Yeah, or indeed you carry on with the rest of the work that you've got to carry on with, right? That's just fun. I guess the hardest, and so when it's absolutely clear and everything's going swimmingly well, then that's great. You can sort of be working and doing everything well then. And when it's really closed and like tonight, then you're really not going to do anything, then that's also fine. You can sit there and work in the data room or even in the lounge and just chill out and have a cup of coffee and carry on. The hardest time I find is when there's actually like patchy cloud, because this is really hard to work with. Depends on what type of observing you're doing. If you want to do some types like what the MOA telescope here does, or what lots of astronomers do with doing photometry or brightness measurements of stars, even a little bit of patchy cloud is kind of like, no, that's it. We can't work in that. We need the clearest skies to be able to do what we do. The work that I do actually doesn't really require super clear skies. You can work around a bit of cloud, so long as it's either light or in different parts of the sky than where you're currently pointing.
Is that because you're looking at the spectrum, and so you're not looking necessarily at absolute brightness so much as what are the bits within the spectrum and where are they shifting to over time? So you can get away with a little bit, well, that wasn't the best picture, but we can still get some detail out of it.
Yeah, exactly. I mean, what it really comes down to is, can I get enough photons to make a good spectrum? And on a good clear night, it might take me 20 minutes to get the few million photons that I need to make a really good spectrum. But then on if there's a little bit of haze or a little bit of high cloud, it might take me 25 minutes to do that. But that doesn't matter. I've still got what I need, right? So that's okay. It's when, I guess, you've got a really thick cloud that's kind of just there, and then you've got another one there, and you're trying to figure out, well, there's a clear bit over there. Do I have any stars that's sitting in that bit of the sky?
And how long is that going to be clear for? Is it worth my effort to move over and have a look at that, only to find that by the time I've got the telescope there, it's too late. It's gone.
Or what happens quite a lot in particular this observing run is you get all set up, the first sort of 5 to 10 minutes absolutely fine, and then that cloud that you were trying to avoid has suddenly appeared exactly where you were observing, and so your image is completely washed out.
You must have to cultivate a certain Zen attitude of, oh, well, that's just the way it goes. Because if you took it personally, you could be out there shaking your fist at the sky every bloody night. And there's nothing you can do about it. It's just going to do what it's going to do, right?
That's exactly right. Yeah, you do become a bit kind of, I guess, expect the worst, but then get really happy when you do have the clear skies. And I think we've made a lot of the fact that it's cloudy, and I think that may be a little bit misrepresentative of the observatory generally. I think I've got a bit of a bad luck run at the moment. I do normally get somewhere around 60% clear sky, which is it's good. It's not, the same as being out in the Atacama Desert where it hasn't rained for like 5 years or something. But it's pretty good by New Zealand standards.
But when it does all go smoothly, when it does go nice and swimmingly, and you've got clear skies and you're taking your data and you're on a bit of a roll, it's got to be a nice feeling. It sounds like, even with a bit of bad luck along the way, if you're getting a reasonable run, then it sounds like a pretty good bit of your life to be able to go every once in a while and just, I'm going to go and do this thing. It's part of my job. It's part of the thing that I've been passionate about doing forever. That's got to be nice.
And it's very nice to keep coming back to the same observatory. I mean, I've been working here for about, 12 years now. Since I started my PhD, and the telescope's the same, the spectrograph's the same. It's like an old friend, and when it does work, and then you come to the end of the run, you download your a few gigs of data that you've managed to achieve, hopefully maybe even tens of gigs of data by that time. Then it's nice. It's a really nice feeling, and you sort of know that you're going to come back the next time and get some more.
Close the door and say, see you later, old friend. I'll be back again in another year. How long do you go between observing runs at this place? International travel allowed.
Yeah, I would try and come in between every 1 to 2 years, just because it's trickier for me to get out to New Zealand and with my job in the UK. But it's nice to come back, and then you say it's an old friend, and it's like, I guess, any scientist who's got an instrument that they've worked on a lot. You learn its quirks, you learn its own particular personality that these things have. So this telescope likes to do things some particular ways. It doesn't like it if you set it up in particular ways. It gets really stroppy if you do some things, and it will start grinding and making horrible noises if you try and do others. So you just learn, and you become kind of familiar with each individual instrument.
Well, that brings us to the end of another episode of the podcast, an episode in which I feel like we've learned a lot more about each other. And by each other, I mean I've learned a lot about you. Don't know that you've learned a hell of a lot about me, but I think I can see a lot more about what you do, Emily, both specifically I'm observing you through the Zoom here, and I can see you in the room that you're sitting in. What is the name of the room that you're in?
I'm in the data room. Well, I should spin you around, because actually you haven't got the best view of the room. Let's try this. I just need to bring the cables with you.
Can hear things humming away in the background.
So this is what I'm usually looking at.
Oh, wow. Banks of computer monitors and... Wow, that does look... Yes, that looks proper.
And that's my sort of readout zone of what all the information porting through from the telescope and from the GPS systems and so on coming in.
Yeah, it looks proper technical.
And there's some nice pretty pictures of stars as well.
Because
brighten
you're an astronomer, just in case you needed reminding.
Yeah.
It's been really nice chatting with you about all of this, Emily. I feel like I kind of know just a bit more about what it is that you get up to when you go away on these jaunts overseas, as well as a bit more about why you do what you do, both from a personal and from a professional point of view. So that's been really, really nice. If you out there in Listenerland want to get in touch and say hi and drop Emily a line and say, why don't you try doing it this way? Have you thought about, examining your stars in the following way? Or you could probably do it a bit better this way. Or I've got an idea about data analysis. Or even, I've got an idea about where the universe came from. Do you want to read my theory? Then you could get in touch with us in any one of the following ways. Emily, how can people get in touch with us to do that?
You definitely should email Chris personally at his personal email address.
No. I don't have a personal email address. However, we do have various ways that you can contact us. Give us one of them.
So we are on the interwebs. We are at SyzygyPod. That's at SYZYGYPOD on Twitter. If you dump in SyzygyPod into Facebook, then you'll come up with us as well. And same on the Instagrams.
That's right. Or you can just go to our website, syzygy.fm, where you can find all of the past episodes, the show notes, the fantastic pictures that we put up with every single episode, and a contact form if you want to send us your personal theories of cosmology. Then you can do that as well. You can also check out our Great Wall of Gratitude, which is where we put up all the names of the people who support us financially on the show. And they do that through going to patreon.com/SyzygyPod. There we are again, and you can sign up if you want to become a supporter of the show for just as little as a quid or a dollar or so a week, up to as much as you want to throw our way. Where does that money go? It goes to keep the electrons flowing through the podcast and through the website, and when the world opens back up again, it allows us to go and do things like festivals where we do live shows and performances and so on, and that's great fun. I'm looking forward to doing that again in the future. But of course, the other way that you can support the show, the best way that you can support the show, is just by telling everyone you know that there's this fabulous podcast that you listen to called Syzygy, and they should as well. Leave us a review, leave us some stars on your podcast player of choice. That helps us to rise up through the noise and attract as many listeners as we can to tell them about the wonders of the universe. But we should probably stop it there. So, Emily, you're coming to the end of your run at the observatory. How many more days have you got?
This is my second to last night, so nearly done.
So you're emerging back out into the brightness of day and joining the rest of the world. And then when are you, how long have you got left in New Zealand?
So just a few more weeks now, so I'll be back sort of towards the end of April.
Right. Well, with any luck, we'll fit in another recording or two before you come back. But until then, enjoy the rest of the run. I hope you get some clear skies. Hope you get some proper good data taken. And I look forward to talking to you when you emerge back out into the light.
Yep, I just won't ring you on the grumpy day. How about that?
Yeah, don't do that. Maybe we'll schedule it for after the grumpy day. All right, Emily, until then, I'll catch you later.
See you later.
All right, bye, everybody. I'm very jealous.
It is a lovely place.
I'd kill to get out of my house. I'm just looking at maps at where you are and remembering when Anna and I were there pre-children. This would have been about 2003, and the car that we had borrowed from friends in Christchurch, which was a shitbox old Honda Civic, was already falling apart when we borrowed it, and it really started falling apart. And at the township of Aoraki, the clutch started to go, and so we drove all the way back to Christchurch, not being able to go down out of third gear.
Oh no!
So getting started at all was a challenge. But then we're going through these towns, going, "Get out of the way! We can't slow down." And we got all the way home until we were about 20 k's out of Christchurch, and then we hit traffic, and the bottom almost literally fell out of the car. We just had to get it towed home and say to our friends, "Really sorry, We broke your car.